Okay, I think we're live. Uh, Today's the last lecture in our series. We do have three things left to do. Looking at the schedule, let's go over what those are and how they work. Oh, our camera's pointing up at the ceiling. All right. Um, Today we'll talk about mainly stress concentrations, calculating those by hand. We'll talk a little bit about finite element. We've done several finite element exercises throughout the quarter, just interspersed here and there. I do have SolidWorks open so that we can do one more and try to, compare results from that to the hand calculated results. So today won't take very long on that end. On August the 11th, we can, or you can, retake exam 1 or exam 2, not the exact same exam 1 and exam 2 that you took previously, but you can take one. I do have a questionnaire here on Moodle. It doesn't this doesn't sign you up to take one. It doesn't do anything like that. It's just kind of it mattered more when I was making paper copies of the exams. Now it doesn't matter as much because they're digital in Moodle, so that it's not going to run out of copies of any one. So there is a questionnaire. It doesn't actually matter if you fill it in, and it doesn't lock you into anything either. It's more just to give me an idea of who to expect in the Zoom call. So the retake for exam 1 or 2 will be on August 11th. It does completely replace your previous grade. In the whole history of me doing this, a handful of people have made lower grades, but they have been 1 and 2 points lower, not anything significant lower. Most people make higher. Most people average around 6 points higher. And some people make extremely, improve grades. But I would expect, if you redo one of these, that you will make a few points higher. And the more effort you put into that, obviously the higher it will be. But it does replace the grade. So if somehow you do make lower, it does make a lower, replaces it with a lower grade. So that's August 11th. That's Wednesday. August 12th, the Thursday, is exam 3. We will take that during class, just like exam 1 and 2, and just like the redos. They'll have a Zoom link that you can log into. One Zoom link, whether you're doing exam 1 or exam 2, it doesn't matter. And then August 13th isn't a class day. It is just a day for you to get the lab report turned in. If you are graduating this quarter, I do need to know that because I believe the 13th is the day to turn your grades in. So I do need to know. Normally they send me a list. I haven't seen one yet. Maybe nobody in this course is graduating this summer. But if you are, let me know so that I can make sure that grade's in time. All right. I don't know if there's any other informational type things. The exams are no different than they were. You get the exam 1 and 2 reference sheets off of Moodle. You can use those. You can use a calculator. You turn in your work, written or a scan of your work to try and get some partial credit when it's available. Exam 2 should be graded with all the partial credit installed. If you see any places where there's an error or whatever, let me know so we can fix that. But exam 1, exam 2, those grades should be final. Lab 1 grades are up. I haven't done lab 2 grades. So you should have most of your grades. I don't know if WebWork shows you your grades or not. I am going to change one thing in WebWork. Homework 17 is the beam deflection. That's the one that even I was having trouble getting WebWork to agree down to the decimal that it wanted. So I'm going to reduce, it's worth 56 points. I'm going to reduce it down so that it's a smaller percentage of the whole. That won't show up in WebWork, but when I download the WebWork grades and put them in Excel, instead of making it a possible 56, I'll make it something like 20. Just to reduce the impact of WebWork being very picky on that particular problem set. There are several WebWork numbers that we skipped. So we skipped 6 and 10, 21, 22, 23. Those are the ones I can think of that we skipped. So if you're worried that you'd never finished those or never completed those, it's because we never assigned those. And The challenging problems, they stay open until I think the 13th. And those sets are harder sets, but they do count as points on your final course grade if you complete them. So each set, challenge 1 is 1 point, challenge 2 is 2 points, or is another 1 point, and challenge 3 is a third point. So you can get 3 points through those. That's the only real bonus points that are available. That doesn't remind me of one thing. On this summer outline, these points add up to 106, which there aren't any actual bonus points on this exam, but at one point there was, in the past, years ago, there was. And so what actually happens here is I'm going to take off one of these beam deflection problems to get it down to where it actually adds up to 100. So that will be how that gets handled. And these aren't necessarily like word for word the order that the problems show up on exam 3, but it will be where it's a 100-point exam, not a 106-point exam. All right, so let's get, I think that covers, if I see any questions pop up in chat, I will try to answer them, but that kind of wraps up all of the things that I have thought of or that people have asked recently about the ending of the quarter. So we're going to talk here about these stress concentrations. I do have, if we click on that one, I do have a pretty rough, but a rough chart here, several charts. These are what stress concentration tables might look like. But this particular one has a couple extra equations kind of scattered on it, just as reminders, basically. But what this is each one of these diagrams in here has a particular thing where there's a change in geometry. So let's see if we can zoom in and look at some of those. So here's one. This is a torsion. So this is a shaft with a step on it. We talked about that kind of a while back, where there's oftentimes need for a shoulder to be on a shaft so a gear can ride against that, or a bearing, or maybe you just don't need the strength at that point any longer, and so it's just a smaller diameter. But there's a change in geometry. Anywhere there's a change in geometry like that, you'll have what's called a stress riser, and that means that you will have an increased amount of stress at that transition zone between the larger and the smaller areas. This chart is used to help calculate that increased stress. So it's a multiplier. So this value K over here on the y-axis, it's really small, but this K is how much you would multiply the average stress. So in this case, TC over J, you would multiply it by some number ranging from apparently 1 to 3.2 is what's on our graph anyway. And at this location where the geometry changes from big to little, there would be that many times stress. It'd be that much greater. And so here we've got a flexural type, like a beam, with a change in geometry, big to little. Here's another beam type, so they have moments on them, so it's like a flexural stress. And it has a notch in it. Here's kind of a flat plate with an axial load on it. This chart works for both a circular hole, so a hole drilled in a plate, or a big to little with an axial load. There are lots of these charts. So on your web work, I think you have 3 of these problems to work. The appropriate chart, I think, is just right there in the problem statement. These charts are on the exam references so that you can see them. They're small, but at least on the digital version, you can zoom in and kind of see what's going on there. But let's work out how they work. Let's just use one of these. Actually, let's get a web work example. Here's one right here. And it has the chart kind of crooked, but it's on there. So let's work this and see how they work. Today should be a pretty short day. Here we go. All right, so normally what I would look at this problem, it has an axial load P, which in my case, oh no, that's what we're trying to find, is what's the maximum value for P. So safely supported by a flat steel bar, large and small section. Both sections are 10 millimeters thick. You can kind of see that over here. 40 and 60 millimeters wide, it gives us those. So both of those. Connected by a fillet of radius 10 millimeters. That's That's the radius of this little transition. How sharp is the transition? The sharper it is, so the smaller the radius, then the worse the stress concentration will be. It'll create more stress. Assume the material is brittle. All right, so percent elongation. I don't know if we've used this little symbol before, but this means percent elongation. So basically it's a measure of strain, but in percent. It's less than 5 before it fractures. And it has an ultimate strength of 247 megapascals. So the brittle part here, what that's about is a ductile material with a strain or a stress concentration in it will deform. So, you get a little bit higher stress where the stress riser is located, but that higher stress when a ductile material causes the material to deform and kind of absorb, become more filleted, or it just kind of absorbs that energy that's located at the stress concentration and spreads it out. And so the brittle materials, not being able to deform very much, can't do that. They just break. So that's why this is talking about a brittle material. More ductile steels, although this does say it's a steel, doesn't it? Yeah, it says it's a flat steel bar, but apparently it's a brittle steel of some sort, which you can create with higher concentrations of things that would make it more brittle in an alloy. All right, we have an ultimate strength, so sigma U, of 247. Again, brittle materials, the yield strength is not very meaningful because it doesn't yield very much before it breaks. So we have an ultimate strength. Factor of safety of 1.5 is required, so our sigma allowable is going to equal our, in this case, sigma U divided by our factor of safety. So 247 times 10 to the 6th pascals divided by 1.5. And we can just do that math. Let's see. 247 million divided by 1.5 is 164.7 megapascals, or 164.7 times 10 to the 6 pascals. Okay, now what I want to do is use the equations I already know. So sigma equals force, or P, whichever one you want to use, divided by area. Not sure what happened there to make it move around. Force divided by area, that would be, this is an axial force, so I'm calculating an axial stress. And I want to take the worst case scenario. So I do have that I can see there's a large section, 60 by 10 millimeters squared, and a smaller section, 40 by 10 millimeters squared. So the smaller section will just by default have a higher stress. So I'm going to calculate that stress. And well, no, I'm not calculating the stress. I'm calculating the force from that. So actually, let's hold off on that just a little bit because we still need to apply our factor of safety. This is the equation I want to work with, but we need to figure out what our multiplier is going to be. So what is K going to be at? Basically we're talking about this location or this one, where that stress riser is located. So on the chart, I have the top line here. That is if I had drilled a hole in the plate. I don't have a hole in the plate, so I don't use that line. But I have 4 lines that are all labeled capital D over lowercase d. So I do have to check and see. Capital D is the width of the larger section. Lowercase d is the width of the smaller section. So my ratio of D over D is 60, these are millimeters, over 40. Millimeters cancel out, and I just get 6 divided by 4 is 1.5. Okay. Fortunately, there is a line on here that relates to 1.5. That's this line. It is possible that you end up with one that doesn't land exactly on one of the lines, and in that case you have to interpolate between the two. So this one is exactly on a line. I don't have to do any interpolating. So I've figured out what trace I'm working on, this yellow one. Now I want to figure out my x-axis. So that is the fillet radius over the width of the smaller section. So R over D, same units, so 10 millimeters over 40 millimeters is 0.25. I do have to make sure these are in the same units because I need the units to cancel out and just end up with a ratio. So now I go to 0.25 on my chart, which is this line right here. And I look for that intersection. And I see that K for that trace at 0.25 for the ratio between the fillet and the smaller section's width is 1.6. Now I can carry on with my calculation. So sigma equals K times the internal force over the area. I didn't draw a free body diagram of the internal force, but if I were to cut this piece open and look at this piece of it, I have P, and the internal force must also be P. So that's the internal force. Let's fill in the things I know. Sigma is, I have an allowable amount of stress, 164.7 million pascals equals my stress concentration factor, 1.6, times P, that's the thing I'm actually trying to solve for, over A is the area where the force P is located. So that is 40 millimeters by 10 millimeters. And I will need to convert that over to meters, just so I end up with meters being able to cancel out everywhere in my equation. For the pascals over here on the left-hand side is newtons per meter squared. So 1 meter is 1,000 millimeters. And I have 2 of those, so I need to square that conversion factor. All right. 40 times 10 divided by 1,000 2 times 1.6. So I have a coefficient with P now. I need to divide 164,700,000 divided by that factor will give me a value for P that is the maximum force that I can apply before I exceed this factor of safety. That's not right. Why is that not right? Let me run through those numbers again, because something I did somewhere is not right. 40 times 10 should be that. Oh, because that's in the denominator. 1.6 divided by that number, sorry. All right, so I have 4,000 P is equal to this. 616470000 divided by 4,000. All right, this is still a high number, but not as bad as it was before. P is 41.175 kilonewtons. So let's see if WebWork actually agrees with us on that. Oh, gotta log in. And it does. Slightly different number, 41.166. Well, and also this number right here, when I applied the factor of safety, it did have a repeating 6 that I just rounded to 0.7. So there is some rounding in that number. These other, and there's a slight amount, if we really zoomed in on this guy and look at this, K probably is a little bit more, than 1.6. It's like 1.61 maybe, or something like that. So there could be a little bit more that I am kind of rounding on the value of K. All right. So that's kind of how that works. You calculate stress just like you normally would, and then you use the geometry listed on the chart to figure out what trace to use, what your x-axis value is. There's some ratio of the transition fillet. Usually it's a fillet. Sometimes the hole doesn't necessarily have a fillet, but it's the radius of the hole. to some dimension on this smaller piece. That'll give you a value for K, and then you multiply the stress you would normally calculate, the average stress, you multiply that by K, and you end up with your increased stress. So we should be able to take this same geometry, put it into SolidWorks, and get somewhere near the same thing, although I don't know what steel I can put in there that's going to be brittle, so we may not get quite the same thing. It's going to give us a little bit different numbers, but let's just see how we would do this in SolidWorks just to get that done. And we'll create this part. It doesn't give us, I don't think, our dimensions here. Yeah, they don't give us any lengths, so we'll just have to create some reasonable lengths. But just as a way to calculate this thing, let's do it in a front plane. So we'll do something like that, and that, like that. Now let's put some dimensions on there to make this match up. So this is in inches, but this was 60 millimeters. This one was 40 millimeters. That would make this dimension. Did it click? I was trying to dimension a point. That line. I want to dimension that line. It won't really let me. There we go. What is this, 10 millimeters? All right. These dimensions on the length aren't going to matter too much, so I'm just going to leave them the way they are. We have a fillet here on this location and this location. They have a radius of 10 millimeters. Whoops. So that's what it looks like in real life, or at least to scale. And we can extrude that. It said 10 millimeters thick. Yes. So we can extrude that 10 millimeters. And there's the thing that we're actually trying to calculate with. Let's get our simulation open here so that we can run a little simulation on it. While we're waiting on this, since we're talking about finite element also here, these are both ways to get a better answer than what you would have if you just did the axial stress in the thin part of the bar without considering the stress riser at the fillet. We've done some SolidWorks, some finite element analysis in the past. Just to explain some of the terms in there, the thing that's going to happen is we're going to apply a mesh. And the mesh is instead of looking at this as one big piece of metal, we look at it as lots of little elements. They're called elements, finite element, that create this same shape. And by doing that, we can look at individual responses of elements to kind of create a bigger picture of what's going on in the whole item. It's kind of like, instead of looking at a wall, you look at individual bricks in the wall and how is each one of those bricks responding. And each brick is interfacing with its neighbors and influencing them, and they're being influenced by its neighbors. So it's kind of like that. Let's see. We've got our simulation. Yeah, there it is. New study. We will do a static study. No sense in doing any transient stuff. Let's apply a material. There's a cast steel that will have some amount of brittleness to it. We just use that. Fixtures, we will fix one side. So in our WebWork picture, it just showed forces, axial forces on either end. We'll replace one of these forces with a fixed surface. So like this force is the reaction to this being attached to something. So we will just pick this surface and fix it totally. And over here, we will apply a force on this surface. but we want a tensile force, so let's reverse the direction, and let's make this force. Oh no, we actually do want SI units. Let's make this force the, what was it, 41,175 newtons. And there's newtons. Okay. So we're doing this one backwards from the way that we did the web work problem. The web work problem wanted us to find the force that we could apply. This one, we're applying that force and seeing if we get the same kind of stress. So the stress that we're looking for is, well, let's see, it's going to be on here. 165 megapascals at the little corners here. Let's mesh and run. This shouldn't be a complicated there. It's already done. Now I did get a very different number here. But let's see if I can. So I got 2.264 times 10 to the 8th, where I shouldn't have more than 2.5 times 10 to the 8th. Well, no, 1.6 times 10 to the 8th after we apply our factor of safety. The difference here is the fact that, let's see if we can see it. See how this material was able to deform? The brittle material would have trouble doing that. Now this is multiplied 200 times, so it didn't deform that much, but when you exaggerate it, you can kind of see what it wants to do. It did predict that the high stress is in that location where we thought it would be. It predicted a much higher stress for this amount of force, but if I hover over here, you can see the amount of deformation, again, 200 times what it really is. But you can kind of see and how a more ductile material is going to flow and reduce, just naturally reduce the effect of these stress risers. Because there's the original outline, and here's where we are over here. So there is a lot of like give that is happening in a ductile material. I don't really even have one listed here that is, I wonder if I can, how long it's going to take to open this up. Sometimes opening this window takes a really long time. We'll give it a second and see if it can apply a material that maybe like a cast iron or something. It blinked, but I don't see my window. There it is. All right. These are all steels. There's an iron. Gray cast iron is not going to be very ductile. So let's see what we get when we run that one. In fact, it says, it shows that all of the results are not valid anymore. Well, I still get, still trying to show some ductility here, even with less. Well, let's see, where's my original shape? Still showing a lot of ductility in that that I don't think should be there, but this is also why some of your simulations aren't always perfect. And I'm getting a much different number over here. Well, no, not much. 2.2, 2.3, and I should have 1.6. So they're not orders of magnitude different, but there is a difference. So you can't trust completely either one of these methods. But there is a by hand way to get a better estimate of the stress. The stress that we would have calculated is way below all of these. And then there's the other thing with this finite element is that, see how it's really blocky in here? Typically finite element will give you the very maximum stress up here is going to be a very, very localized thing. So like at some one individual little point somewhere. So if I do look and see the color in here is actually more like an orange. If I kind of average it all together, I can get a better average if I increase the mesh. In fact, maybe I'll do that in a second. And not look at just the peak over here. And the oranges are, now I'm in the 1.8s or so. Maybe a 2. So I'm getting closer to the thing. Let's increase our mesh. Let's do the mesh advisor. That'll just let me move the slider over and I can get a little more. Oh, no, that's this thing. Never mind. Let's not do the mesh advisor. Maybe it's create mesh. There we go. We will move it a little bit over here to the fine side. You can actually see, yeah, it shows up a little bit. You can see, it's kind of hard to see, but because it's a dark blue on a dark gray. But you can see the elements in there. There are not a lot of elements in this location where I'm trying to calculate this stress. And so when you're doing something like this, a better simulation version, so SolidWorks or ANSYS or anything like that, is going to be to increase the number of mesh elements in the particular location that you're interested in. So we have apply mesh control, and I could select this entity over here and see it's given me these little, I don't know, nodes where it's going to increase the density of them. Or I can just specify, let's see, I want them, let's see, this was a 10 millimeter radius. Let's say that I want them spaced out every ½ millimeter. So now we need to, I think that should do it. Let's see if we can create mesh with that. Oh no, that's not mesh. I just want to mesh the thing. So, well, so it kind of helped. See what it did? It put the elements right here, but then they still ended up kind of spreading back out. So let's add a few more mesh controls. And let's add them to this line, and this line. All of them on the, what I do, ½ millimeter spacing. And let's see if we can get a little bit more detail. I might have to do some different ones on these lines, but let's see. See what we get. So it's starting to put in more and more detail in there. It's still not as much as I would like in there. I would need to create a little bit more control in there, but let's just quit fiddling with it and run the thing. I guess I could have just run it. I don't need to remesh it. It's taking a little bit longer to run. And now when I look at, well, let's look at our stress again. I have a much better, you know, resolution on the stress that's in here. I still have that higher number, so there is still prediction that the stress is going to be higher than what I calculate when I use the chart here, but at least I have a better sense of what's going on there. And you know, what color is that? Maybe the 2.5 color somewhere in there. I could probe it and actually ask, you know, what is the stress at these different locations. That's getting a little beyond what our goal is here. You're not going to have to do a SolidWorks simulation on exam 3, but you might have to answer questions like when you're doing finite element analysis, you create a mesh. You apply constraints to hold the mesh in space. You can apply external loads and forces and pressures and all sorts of different things like that. The mesh is made of elements. Elements are connected at vertices. You know, things like that might be types of questions you would have to respond to. All right, I think we're good. I think we're good with SolidWorks. We're going to close that down. We don't need to save that either. Why don't we do one more of these just to have one more under our belt? And I think that's going to be it. That'll be the last topic that we need to cover for our entire quarter. Got some tests to take, but that should do it for us. All right, let's do this one. Okay, copy that, and we'll put it over here. This one's a flexural stress. We have a beam. So just to clarify, on the exam, so these WebWork problems give you the chart right there with it. On the exam, you won't necessarily have the chart in the problem statement. So you might have to go figure out which chart you need to use. The charts are all in the exam references, but it won't necessarily be right there in the problem statement. So don't count on that. You do need to know which one of these applies to which situation. All right, so we have a beam, 180 newtons. These grooves, these little grooves right here that are cut into one end of it are 10 millimeters deep. They are 1 meter from the load, so this labeled as 1 meter. Determine the smallest allowable width, so how wide. Basically, you can see the dimension over here is the radius of the groove. So how big is that radius? Smallest allowable width of the grooves if the allowable stress in the bar is 150 megapascals. The smallest allowable width? Well, that seems to... Well, all right. Well, we want to find out the width of groups. Seems like it should be the largest allowable, but whatever. We're going to neglect the effect of shear stress due to bending. Whenever you do have bending, there is a shear stress, a direct and a secondary shear stress. We're ignoring those. All right, here's our little chart. And we can get started with calculating some things. So allowable stress, like we had last time, this one's just given. Sigma allowable equals 150 megapascals. Well, last time we had to apply a factor of safety. This time they just tell us the allowable stress. All right. This is a flexural stress. Sigma equals MC over I would be a flexural stress equation for a beam. The moment that is created at the little notches is this 180 Newton force times 1 meter. So we can deal with that. Moment equals 180 Newton meters. 180 newtons times 1 meter, 180 Newton meters. That's the bending moment if we were to, cut this thing open right here and solve for the internal bending moment. All right. C is the distance from the neutral axis. Well, it's labeled right here, in fact. The distance of the neutral axis to the point of interest. The point of interest is going to be the bottom of the little groove here. So, and they just show us over here what C is. C is 20 millimeters, it looks like. Let me see how this is. Yeah, the 10 millimeters is to the very bottom of the groove into the bar. And so this distance, whoa, wow, that's getting crazy on me, is 30 millimeters. And take off 10, so we left with 20. So C is 20 millimeters. I is the moment of inertia for the beam. So this little picture is a cross section of the beam. It's just a flat beam. These little parts here and here are showing kind of the inside of the groove. So the I that we need is the moment of inertia of this green rectangle about its own neutral axis. The neutral axis being that axis right there. We don't even have to calculate it because it's symmetric. So I is a moment of inertia of a rectangle where there's a base of 9 millimeters times BH cubed. So H is 40 millimeters. BH cubed over 12. And we need to calculate that number. So let's see. Calculator went off. 40 cubed times 9 divided by 12, but that's in millimeters to the fourth. So 48,000 millimeters to the fourth power. Okay. MC and I. All right, and then we need to figure out what our multiplier is. We have everything except basically, what are we trying to solve for? Oh yeah, we're trying to solve for the radius of the thing, which is going to be on our chart over here. So, that's an interesting one. I've got to think about how we're going to do this. Let's see which chart trace we're on. D over D is 60, and lowercase d is 40. So 6 divided by 4 is 1.5. So we're on the 1.5 track. And I think what we need to do is solve for K first, and then we'll back out from there. So sigma allowable is 150 times 10 to the 6th, that's a 6, megapascals equals K, which we don't know, times M is 180 Newton meters. C is 20 millimeters times 1 meter is 1,000 millimeters over 48,000 millimeters to the 4th with its conversion factor. Okay, so let's see what we can do here. 48,000 divided by 1,000 to the 4th. 180 times 20 divided by 1,000 divided by my denominator. All right, to get a big number, let's see, that's 75 million. So 150 times 10 to the 6th megapascals equals K times 75 times 10 to the 6th megapascals would be those units also, I think. Should be. So 150 divided by 75 is 2. So K equals 2. So we go to K equals 2, intersect that with our line, which, let's zoom in a little bit on that. So that's this point right here. And let's go down here. That is a R over D ratio of 0.1. Okay. So R over D equals 0.1 equals R, which we don't know, over lowercase d, which is 40. Therefore, R equals 0.1 times 40, which is 4. And this is millimeters here. So R is 4 millimeters. The question is, determine the smallest allowable width of the groove. If we look at the groove width is actually 2R, so looks like it's going to be 8 millimeters. Let's see. Well, and it even says over here 2R equals 8 millimeters. And we are correct. Maybe the only one we ever got exactly correct. The last one we worked. So that one's a little bit more complicated. You know, you got to figure out that you can even do this direction where you solve for K and then figure out what some of these ratios must have been if you know the value for K. So that's a little bit different way of going about doing it. This is more of a design problem where we're designing a feature on the this bar versus the others are typically more analysis problems. We've got the bar all well defined and we're trying to analyze either a stress at a location or how much force it can hold or something like that. So this is a little bit more of a design problem. All right. I think that is going to give us a good setup. There will be, let me check that before I tell you that for sure. Did I put a stress concentration problem? I know there's some on web work. Yeah, there's one of these problems in the medium level kind of problem on the exam. So there's one to work on. All right. I think that does it. I think we covered all our material. We've got everything. You've got a couple of days left to finish up web work. Like I said, there are some web work problems. I've had questions about 6, 10, 21, 22, 23. Those may look like they're on your web work enclosed, and you never did them. That's because I never assigned them, so you don't have to go back and try and do those. They were either redundant or stuff we didn't really talk about, or whatever reason, those never were assigned. I will see y'all in Zoom on Wednesday, those of you that want to do a retake. Thursday, I'll see all of you. And then Friday, I won't see you, but hopefully you get your final reports turned in by then. Again, if any of you have you're graduating this summer, I need to know that just because your grades are going to be due a little before everybody else is, and so I need to get those in, make sure that you actually graduate. So let me know if you are graduating this summer so that I can go ahead and do those grades before everybody else's. All right, I don't see any questions going on in the chat, so I think we're good there. You can still send me some email. I still have a few office hours left in the week, and we'll go from there. I will see y'all on Wednesday or Thursday or both. See y'all later.